Okay, this podcast is on equilibrium reactions. These are reactions that are actually reversible, and a good number of those in chemistry are just that, reversible. As you can see from the three shown on this slide, three reactions that I've shown involve chemical reactions. For example, the blue-colored cobalt chloride anhydrous substance can be converted into the pink-colored flower that hangs in the classroom easily by adding water. Pink to blue, blue to pink, adding and removing water, adding or removing heat can convert one form, the hydrated copper chloride, into the anhydrous. Solubility is another substance that's easily reversible. If you have a saturated solution of lead chloride, if in this case, because the dissolving is an endothermic reaction, raising the temperature can bring about more ions of lead and chloride in solution. And then finally, one that I hope to show you soon is the color change between the chromate and the dichromate ion. It is temperature dependent. Oh, now looking at it, I can see that, sure, this reaction is not balanced, but that's okay. It is definitely pH dependent. Again, not only chemical changes, but physical changes are reversible. And there's all kinds of examples here given, but the important thing is that when a system is at equilibrium, we have a forward and a reverse reaction rate that are equal. When those reaction rates are equal, it's important to remember that even though a lot of the observations don't change, humidity, vapor pressure, amount of solid, color, there is a dynamic situation. In other words, there is constant forward and reverse motion. Recall this slide from a previous chapter on kinetics, and if we look at the activation energy shown in the graph of the forward reaction versus the activation energy of the reverse reaction, you can see that the forward reaction has extremely large activation energy while the reverse reaction has a very small, by comparison, activation energy. When this reaction, whatever it is, if it's a reversible one, is at equilibrium, the rate of the reverse reaction seems a lot easier than the forward reaction. At equilibrium, when the rates have equilibrated, then will you have more reactants or more products? It seems pretty easy to see that it's hard for the reactants to turn into products. So in this equilibrium situation, the products would be favored as opposed to the reactants. And that's a common question that we ask about equilibrium reactions. Is it reactant favored or product favored? If we talk about which side predominates, reactants or products, probably understanding that HCl is a strong acid would help us to understand that an aqueous solution of hydrochloric acid would produce primarily ions. Conversely, a weak acid such as acetic acid, this would be reactant favored with very few ions and mostly molecules. So how do we determine whether a system is at equilibrium if it's constantly changing? Well, we look at the macroscopic observations that do appear constant at equilibrium. It's important to remember that change is constantly going on even if you don't see a change. We can easily use a spectrophotometer to record the color. We can use a pressure probe or a temperature probe to monitor those two variables, or we can look at the amount of solid that is present in a container to know whether it's increasing or decreasing or staying the same. Things that stay the same or are constant would be one sign that the system's at equilibrium. So this quarter, what I've started to do is explain the meaning of equilibrium. We're going to move next into what does an equilibrium constant, capital K, mean. We're going to talk about calculations for calculating K from concentrations and then using K. The next podcast, if there is one, and the last concept will not be the subject of this video, but the first 3 bullets will be addressed. So going back to this slide, if the equilibrium constant is written with the products multiplied together divided by the reactants raised to the power of their coefficients, and in this case with equilibrium it is products over reactants, since hydrochloric acid is strong, we'd have many products, very few reactants. This means that K would be a large number, a number much larger than 1, sometimes on the order of 10 to the 10th or more. Conversely, if you have an equilibrium system where the reactants predominate, then you have a large number in the denominator, small number in the numerator, and so the numerical value of K is much less than 1. K is never a negative number. K is always a positive number. It's either going to be small or large by comparison. In general, we have K, just the general capital K, but depending on whether we're working with solutions or a total gaseous equilibrium, we might use Kc for concentration, or equilibrium in pressure. More on that later. So, more of the same slide, mostly ions. Products will dominate. K will be greater than 1. So if you look at this equilibrium situation, the numerical value for K is given. Because K is less than 1, that implies that hydrogen iodide would be favored. The reactants are favored. The equilibrium equation. Notice a couple of things about this. We have products over reactants. They're multiplied together. Their concentrations divided by the products over reactants. Since HI is a reactant, it's in the denominator. Notice the power. It's raised to the second power, and that is because of the coefficient of 2 in front of hydrogen iodide. So let's start with a simple problem where we start off with 0.3 moles of hydrogen iodide in 5 liters, and I'm going to ask you to graph. So in your notes, graph what happens to the concentration of HI over time, what happens to the concentration of H2 and I2, how are they related in terms of stoichiometry. Concentration units that we're looking at are definitely in molarity. I'm not asking you to put numerical values on the time axis, but can you make a graph? Bring that in as the first of the requirements for your homework. What does that graph look like? What happens over time to the concentration of HI? What is the slope like for I2 relative to HI? If we approach this problem, though, from the standpoint of equilibrium, then a quantitative look as opposed to a qualitative graphical look is what's in order. For the next slide, what we're doing is we're starting with this same problem. And of course, did you calculate? Initial concentration was moles per liter, 0.06 molar. If that's the only thing in the container to begin with, then we had 0 initial hydrogen ions and 0 iodide ions to begin with. This table is sometimes called an ice table. It's called an ice table because it has a way to organize the information given in the problem. We have the initial concentrations, the change in concentrations, and then the equilibrium concentration. For this problem, we're given K. So given K, we're trying to calculate the concentrations at equilibrium. Well, what we don't know is how much change occurs. So we'll let X be our variable. Since there are no products, the HI has to decrease. So we're going to subtract our amount of HI and add to our amount of hydrogen and iodide. Notice the coefficient of 2 in front. Notice the minus sign because HI is being used up. The the stoichiometry in this reaction, the coefficients in the balanced equation, help us when we're setting up our X. So for every 2 moles of HI that decompose, we form 1 mole of H and 1 mole of I. That is our X, and that's how we set up our proportion. Now we'll simply do the math and subtract. Once we have this, since this is called an equilibrium constant here, which is a value of 0.01, we put products over reactants. So we can substitute into this equation X times X over 0.060 minus 2X squared. And that equals the value of K, which was 0.01, if I'm remembering correctly. Well, if you look at it, you've got a perfect square, don't you? And if you're going to square one side, you might as well square both sides. So really, this line should be extended all the way over to both sides of the equation. Take the square root of both sides. That'll simplify the math so that you can calculate the value of X. So that's the second assignment for you to do. Calculate the value of X and then substitute those values into the equilibrium quantities and tell me at equilibrium the concentration, as the question at the top of the page indicates, the concentration of HI, the concentration of I2 and H2 at equilibrium. All right, now we have a new problem. This problem is an example of calculating K from equilibrium data. Since it's an equilibrium constant, it means that if you know the equilibrium concentrations, you can actually calculate the numerical value of K. Once the value of K has been determined, you can use the information presented in problem 2 to calculate the equilibrium concentrations of N2O4 and NO2 when you start the reaction with pure N2O4. So follow the steps outlined in red to complete the second problem. Bring this in as another part of your homework assignment for tonight. Another thing that can be done in addition to calculating K, calculating equilibrium concentrations, is manipulating K. And by that I mean, you know how we did Hess's law, we had an equation. If we flip the equation around, we change this sign. If we multiplied the coefficients by 2, we manipulated K. But knowing that equilibrium is really a ratio of products over reactants, the tools to manipulate are a little bit more complicated. So with the given equation, now we've flipped it around, the numerical value of K, it could be a different value than the previous problem because K values are very temperature dependent. More on that later on. But for this problem, for this equilibrium, the numerical value of K is 0.2 as written. And if I take the equation and flip it around, what is the numerical value of K? It's important to remember that since this is a ratio, if we flip this equation, now what was products becomes reactants, and what was reactants become products. So when you do this problem and you manipulate K, pause the podcast and see if you can figure out, what's commonly called K prime. Not only for the first equation, but look at the second one. When you multiply everything through by 2, how does that change? Does it double the value of K? Try writing the equilibrium equation for both the original and the 2 altered ones, and you'll see the mathematical equation. Pause and come back. Okay, have you got it? How did you do? Does that make sense? If you're still not clear, let's go on to the next slide. Remember, if this is turned upside down, as I've shown you here, then if this is going on its head, then this number has to go on its head as well. So you'd be taking the inverse of K. Here, this is actually, the coefficients have been what? squared. The second manipulation of K involves the conversion between Kc and Kp. Kc being concentration and molarity, Kp is expressed in units of pressure. And although equilibrium constants do not have a unit in general, the one exception is with regard to Kp. When you're calculating Kp, it is important to clarify whether these units of pressure are in atmospheres, millimeters of mercury, torr, kilopascals, etc. So what I've got here on this slide is a derivation of how we get from Kc to Kp and back. So if you rewrite the first equation, products over reactants, and this works for gaseous equilibriums only, you can rewrite molarity in such a fashion as I've done here. And then if you manipulate the ideal gas equation, isn't N over V simply molarity? So since this is molarity and this is molarity, we can plug pressure over RT into this equation for Kc. And we have the equation on the right-hand side. After we do that, we can simplify and combine like terms to get this equation as shown here, where we moved all the pressures together, we moved the RTs together, and we ended up with something like this, and then we simplified. Bottom line is that Kc equals Kp times RT times the change, products minus reactants, if you look at the overall equation of the moles of gas. So since we had 4 moles of gaseous products minus reactants, that's the equation. I like non-negative numbers, so I have it written Kp equals Kc times RT, and then it's, instead of a negative change in the number of moles, it's final minus initial number of moles. So can you take that information and apply it to this situation here? Can you write an equation for homework of Kc? Okay, to review a few things, we have a situation where given the initial concentration now of 2 reactants, we know that since there's no products, the system is not at equilibrium. So we know for a fact that the reactants have to be used up and we have to turn them into products. If there was some of everything, that would be a different situation in the next scenario. You can pause this podcast and cover up the table to make sure that you would be able to follow the initial concentrations, know the mole ratio as shown from the stoichiometry, be able to apply it to calculate the equilibrium concentrations, and then go ahead, plug in the equilibrium concentrations into the equilibrium constant expression, products over reactants equal the numerical value of K, and solve for the equilibrium concentration of all species. It's important to be able to see shortcuts when they're available. Did you see it when solving? Did you see that it is a nice perfect square? That should simplify your math tremendously. Make sure you're aware and attuned to those methods of simplification. So a common question that's always asked is, how do you know whether you're subtracting X from the reactant side or the product side? And the answer to that question is it depends on whether you have too many reactants or too many products. A mathematical analysis of this should help you to understand that. When the numerical value of Q is exceedingly large, that means products over reactants, that the amount of products is too great. The reaction needs to go in the reverse direction. When Q is less than K, then the reaction needs to move forward. And when Q equals K, the system is indeed at equilibrium. So here's another scenario. Now you have all of the reactants and products for this system. So first of all, calculate Q, decide if it's at equilibrium. Then decide the direction of change, set up your ice table, and calculate at equilibrium the equilibrium concentrations of all species. That's a homework assignment. Notice this equilibrium constant expression, K equals calcium ions times carbonate ions. What has been left off is the calcium carbonate. It turns out that both solids and liquids are not included in the equilibrium constant expression. Hopefully you know the answer to the question, why? The source has to do with the fact that if you have a pure sample of calcium carbonate, its concentration, whether you have a lot of it or a little bit, is constant. As opposed to an aqueous solution, its concentration can vary. So liquids and solids are not included. Gases are, though, because we can change the pressure or the volume of a container of a gas and thereby change its concentration. So in equilibrium constant expressions, aqueous solutions and gaseous material are included in the expression, but solids and liquids are not shown. Just a side joke. Concentrated water. Be careful. It could be dangerous. Here's another homework problem. Pause the podcast. Calculate the information asked in the problem. Sometimes the mathematics of an equilibrium problem are a little bit more complicated and require the use of a quadratic equation. If you don't have that set up on your calculator, you should do so at this time. Take a minute to review the setup of this, making sure that you understand the process. And you can see how when you have an equation that looks like this, it will require putting it into the proper quadratic form and then solving for x. Not a process that you can imagine having to do on tests or quizzes very often, but if you need to do some homework problems, make sure you have that equation installed onto your calculator. One final problem solving to go through, and this actually makes the math a little bit easier. So if we take something like acetic acid, which is a weak acid, its numerical value for K is a number smaller than 1. By the way, equilibrium constants for acids, as we'll find out in the next chapter, have a symbol of K sub A, for A is for acid. The expression products of a reactant is written as shown, and you're going to be asked to calculate the pH of a 1 molar solution of acetic acid in these kind of problems. Well, if we go and set up the problem, it does look like it's going to require the use of the quadratic equation again. However, because the acid is such a weak acid, the value of x relative to 1.0 is small. So in terms of sig figs, once you calculate x and subtract it from 1.0, you've still got 1.0 again. So this problem actually simplifies to x squared over 1.0, as shown over here. X squared over 1.0, which then makes your mathematics very easy. And looking at the numerical value of x, you can see that that number is small relative to the original concentration. So there's very few hydrogen ions. I bet you could have seen how to get to pH from there, the negative log of the hydrogen ion. So the general rule of thumb that you might want to remember when trying to neglect x is that if the concentration of the original solution is on the order of 10 to the 4 times the value of K or more, then it's okay to neglect this x, that it will be you will be able to simplify the problem in that manner. So with the new situation, instead of having just acetic acid in our solution, we have something that contains both acetic acid and sodium acetate. So we put those both in 1 molar concentration into a solution, and so the initial concentration of the acid and its conjugate base, if you remember that term from the past, we'll be getting into that later, are given as the initial amounts. So can you apply the same concept that was just introduced and calculate the value of X, simplifying, using the simplifying method, and then solve for pH? Bring in your answer to that problem as well. Thank you. Have a good night.